Hello! In this video, we're going to start to talk about using truth tables for lots of different sentences. We're going to build up to that, however, and what we're going to learn in this specific video is how to calculate the value that a sentence has on a particular truth table row. So let's get going with that. Remember, in the end, we're interested in finding about whether or not a sentence is a tautology, whether or not it's true in every situation. And we're going to use truth tables to find that out. That's what we're in the process of learning how to do. So, the thing is, there's so many situations, right? There are infinitely many possible situations, many different possible worlds, and we can't look at each one of them. There are too many of them, and so we have to find out some way to show that a sentence is true in every possible situation without looking at all of them. And we've seen how we do that. We divide all the situations into 1 or 2 or 3 or 4 kinds. So to talk more about that and how we're going to do that, I need some terminology. So we'll say that a sentence is true. That's the same thing as saying that the sentence has the truth value true. And a sentence is false. Another way we can say that is the sentence has the truth value false. It's going to be convenient to talk about truth values, which is why we're introducing this terminology. And we're going to assume that there are 2 truth values, true or false. There's not another truth value partially true. There are not a whole bunch of truth values, mostly true, somewhat true. We're just going to assume that there are exactly 2, true and false. And we're going to assume as well that each sentence has exactly 1 truth value. So a sentence is true and not false, or false and not true. These are substantial assumptions. We could relax them, and then we'd have a more complicated system. We're just going to work with this system where each sentence has exactly 1 truth value. Either it's true or it's false, and not both. Okay, so we call this classical bivalence. Bivalence meaning 2 values. So now let's look at how truth values work in trees. So here we have the sentence P or Q or not R. And that has 2 parts, the part P or Q and the part not R. P or Q has 2 parts, P and Q. Not R has 1 part, R. And then P, Q, and R do not have parts. So this is the parsing tree for this sentence. It's broken down into its components. Now suppose we consider the situation where P is true, and Q is false, and R is true. Well, in that situation, P or Q would be true because P is true. Not R would be false because R is true. And so the whole sentence is true because the P or Q is true. So the truth values start at the bottom of the tree at the sentence letters, and then they go up the tree. So let's take a look at that in the module. So here we have the same sentence, P or Q or not R. And we have this big table. Now, the situation we were looking at, P was true, and Q was false, and R was true. If we click on this question, so this is that row, right, where P is true, and Q is false, and R is true. On no other rows do P, Q, and R have those same truth values. So if we click on the question mark, then we get that tree, right, that we saw in the PowerPoint. So if we look over here, we have P is true, and Q is false, and R is true. So we say, okay, so if P is So what we have is true or false, right? Because P is true and Q is false. So true or false is true. Here we have true. So we have negation of true, and that means negation that this is false. And now we look at the whole thing. Now that we figured out these truth values, and we say, okay, well, P or Q is the left side, not R is the right side of the disjunction. So we have true or false, and true or false is true. So we have the same truth values as we did. So if you look, we have true or false for P, or we have true for P or Q and false for not R. That's what we have, true for P or Q, false for not R. And then we have true for the whole thing. We have true for the whole thing. So what we see here, this is the way we're going to be working on truth tables. We're going to go to a row of the table, and we'll click the question mark, and that will open up this tree. And these values here will come from the row. So P is true, Q is false, R is true. That's because R is true here. And then we calculate these values. And if we make a mistake, it tells us we made a mistake. So, oh, F, that's not right. And this T also turns red. Why does it turn red? It's correct, but it's not correct if both of the parts are false. So this is actually true, but it clashes with this. Once we change this back to true, then this is okay. Okay, so that's how we do one row. Now, there are a couple things that don't matter. when we calculate the truth value of that whole sentence, P or Q or not R. What do P and Q and R mean? We don't care because the truth values don't care. It doesn't matter what P or Q mean to know whether or not P or Q is true. It only matters whether P and Q are true or false or whatever. Their truth values matter. What the sentences mean, what the atomic sentences mean, doesn't matter. And same for R. So whatever P and Q, R mean, we know that when P is true and Q is false and R is true, the whole thing is true, whatever P, Q, and R mean. It's not just that, though. Here's another sentence that looks the same, but it's got Z's and U's and Y's in it. And let's say we said Z was true just like P was true in the first one, and U is true just like Q was true in the first one, and Y is true just like R is true in the first one. Well, then the same thing happens going up the tree. Z or U is going to be true because its left disjunct is true. Not Y is going to be false because Y is true. And now the whole thing is going to be true because Z or U is true and it's a disjunction. And we can see the same thing in the module. So here we have Z or U or not Y. And again, we'll go to the row where Z is true and U is false and Y is true. And we'll click on the question mark and that opens up the tree. And we say, okay, Z or U. Well, Z is true and U is false. So true or false is true. Y is true. Negation of true is false because negation flips the truth value. So now we have Z or U being one part, the left part being true and the right part being false. So we have true or false, and true or false is again true. And so also, right, again we see here the whole sentence comes out true. And what this tells us is not only does it not matter what P, Q, and R mean, it doesn't even matter that it's P, Q, and R in the sentence. Whether we put P, Q, and R in, or Z, U, and Y in, what matters is what truth values the atomic parts have, not which ones the sentence is built up of. Is it Z? Is it P? Who cares? Just tell me whether or not Z or P or whatever is true. Tell me whether or not Q or U is true, and then I'll tell you whether or not the whole thing is true. So what this is an example of is something called truth functionality. The logical language is really special in this way. So every logical sentence is like P or Q or not R in the following way. The truth value of the whole thing depends only on the truth values of the atomic parts, nothing, and the meanings of the symbols. But once you fix the meanings of the symbols, all you need to know are what are the truth values of the atomic parts. And sentences like that are called truth functional. Once you say what the sentence is and say what the meanings of the logical words are, then the only other thing you need to know are the truth values of the atomic parts, and you can figure out what the truth value of the whole thing is. English and other natural languages are not in general like this. Of course, they have words like or, but they also have many other sentences. Many English sentences are not truth functional. So let's say we say, I have a shadow because the light is on. That's true, right? I do have a shadow and the light is on. And not only do I have a shadow and the light is on, but it's because of where the light is and the fact that it's on that I do have a shadow. So this because sentence, this is true. But now let's say, consider this sentence. I have a shadow because I lived in Boston. Well, I have a shadow, that's true. I lived in Boston, that's also true. Don't live there anymore, but I used to. So both of the parts of the because sentence are true, but the because sentence isn't true. It's false. It's not true that, why do I have a shadow? Not because I lived in Boston. So note that in both sentences, the parts are true. I have a shadow, the light is on, I lived in Boston. They're all true. So in both of the because sentences, all the parts are true, but the because sentences have different truth values. One is true, the other is false. So for a because sentence, it's not enough to know, are the parts true, are the parts false? You have to know how the parts are related, beyond knowing whether or not they're true or false. In the logical language, that's not true. You don't need to know about how the parts are related. All you need to know is, are the parts true, are the parts false? And that's what we mean by saying it's truth functional. So this truth functionality is really important because it basically guides how we figure out whether or not a sentence of our logical language is true in any particular situation. So let's say we wanted to know whether or not negation P or Q is true in a particular situation. Well, there are just two things to do. You find out the truth values of P and Q in that situation, and then using the tree, the grammatical tree of negation P or Q, and the definitions of negation and of disjunction, we figure out the truth value of not P, and then the truth value of not P or Q, and then we're done. And we can do that. That's all we have to do because negation P or Q is truth functional. So the question we've been asking in this video is, how do we find out whether or not a sentence is true on a row? So on a row of a truth table, what happens? Well, we start with truth values assigned to the sentence letters in the big sentence that we care about. So say P is true and Q is false and R is true, or P and Q and R are all true, or P and Q are true but R is false, or whatever. And then we want to know, well, what is the truth value of the whole sentence on that row? What is the truth value of the whole sentence when P, Q, and R have those truth values? Well, the truth values go up the tree, starting from the sentence letters and going up to the sentence we actually care about. So in the program, what do? We want to know whether or not a sentence is true on a row. We figure out the truth values going up the tree. And we do that by starting with the truth values at the bottom of the ones that are assigned to the sentence letters, because that's what the row does. And then we use the definitions of negation and conjunction and disjunction, which tell us how the truth value of a conjunction or disjunction or negation depends upon the truth values of its parts. And we just go up the tree until we get to the top of the tree, and then we figured out the truth value of the sentence on that row. Now, the big question we want to know is the sentence a tautology or not? And so we might ask, well, how would we do that? Because I haven't talked about that. I've talked about truth values on rows. Well, that's a good question, and we'll get to the question, how do I know whether or not a sentence is a tautology or not, in the last video of this module, the next video. So go check that out.